Right, so the next speaker is Kiarash Naderi. He'll tell us about 2D symmetric orbifolds and AdS3 CFT2.
Thank you. I want to talk about the status of a project that I've been working on with Matthias and Bob Knighton. And this is still a work in progress. Okay, so we want to understand the gauge string correspondence from the worksheet. And one possible strategy is to start with low-dimensional examples. And as we just had a talk before, one nice example is considering these pure bosonic 2D angles, because the partition function is calculated, like there is an exact expression for the partition function. And Gross and Taylor showed that the partition function, if I consider the large and expansion, is a sum over covering maps. So, and the goal is to find the worksheet description of these 2D angles. So if you want to find the worksheet description, because the partition function is a sum over covering maps, we should find the worksheet description that localizes to covering maps. On the other hand, there is this tensionless string theory on the AdS3 that was found by Eberhard, Gabriel, and Gopakuma, that in this string theory, the correlation function is localized to the covering maps. So then the question that we wanted to answer is that can one gets inspired by this worksheet theory to find the worksheet dual for the 2D angles? Just to mention that here the dual CFT is a symmetric orbifold. Okay, so this is a summary of what I'm going to talk about. First, I will start with the subsector of the 2D angles. It's a chiral 2D angle. Then I go to the free limit. And then I discuss how it can be related to a symmetric orbifold. And then in the second step, we discuss how we can find the worksheet description of this symmetric orbifold. And once we understand how these two are related, we will do the same thing on the worksheet. And we try to reproduce the partition function. Okay, just a quick reminder of, you already heard, but 2D angles. We put the 2D angles on a Riemann surface in Euclidean 2D angles with genus G, the metric A, the metric H, but the area A, the coupling F, gauge group SN, SUN, and the partition function can be calculated exactly. And the important thing is it's a sum over irreducible representations of SUN, and we can label them by the Young tableaus. Okay, so then Gross and Taylor studied the large expansion by fixing the tooth coupling and expanding over 1 over n. And they saw that in the large expansion, there is a sum of, we have to consider the boxes and anti-boxes. And if you only consider the boxes, that gives me the chiral 2D angles in the partition function. So actually, we are interested in the limit of sending the tooth coupling to 0. That's the free chiral 2D angles. And in this paper, it was shown that the partition function can be written in this way. So what it is, it's a sum over, so the 2D angles is on a fixed target space with the genus G. And the partition function is a sum over all the connected coverings of that. And then there's an exponential. So we fix covering space, and then there is a sum over all those coverings with arbitrary branching number and arbitrary number of branch points. And then there are some combinatorial factors associated to each covering. Okay, so then the question is this free 2D angles by any chance related to any symmetric orbifold? In the symmetric orbifold, we have these twisted ground states and twisted sectors. And the partition function, the correlation functions, if I want to calculate the correlation functions of such twisted fields, there is this paper by papers by Lunin and Matur that we should go to the covering space. So the correlation function takes this form, which is a sum over connected covering maps with this branching profile, and then this I of x. By this I mean going to the covering surface and calculating the corresponding correlation function. Okay, so then but as we saw, the 2D angles doesn't have any local degrees of freedom. It's just the combinatorics. So if this duality this relation has any chance to work, X should be a trivial theory. So let's consider X is a trivial theory. It just has one state in its Hilbert space. And for that theory, then the correlation function, this I of X should be just 1. So then the correlation function will be just a sum of this sort. To see this relation a bit more concretely, let's consider the case of a spacetime being torus. And calculate the partition function of free Euler 2D angles. If we go back to the expression, there was this combinatorial factors, but for the torus, none of them appear. So it's a sum over unbranched coverings. So that's the expression I get. And if I now don't have any insertion in the trivial symmetric orbifold, then I will also have sum over unbranched coverings. So we see an agreement in this case. And just to mention, a similar idea has been proposed by Pronovich and Shota before. Okay, so now what about having the 2D angles on a homogeneous surface? What we propose is that the free Euler 2D angles is a deformation of this trivial symmetric orbifold. Thanks. And the deformation is this specific deformation is this deformation. And what it's an integral over the target space of the Ricci curvature times the sigma. And so what we claim is that if I calculate this correlation function in the trivial symmetric orbifold, I will get the partition function of 2D angles. Okay, so now that we discussed the relation between free Euler 2D angles and the symmetric orbifold, now we want to discuss the worldsheet theory that we think is dual to this trivial symmetric orbifold. And then we will do the same deformation on the string side. Okay, so the worldsheet description that we want to talk about is a topological A model that consists of two parts, the matter part and the ghost part. The matter part is a beta-gamma system and a BC system, which I show it by P and theta, and they have these weights 1 and 0, and the central charge of the beta-gamma is 2, this is minus 2. And for the ghosts, I have one BC system, C minus 26, and the opposite statistic, C plus 26. And then in this topological string theory, we should calculate the cohomology and the correlation functions and the observables. I will talk about some checks that we have. So before that, let's discuss the matter part. Let's focus on the matter part and see what we get. The thing is that if I just consider the matter part, I can get a current algebra using this beta gamma system and this p theta system. The current algebra that I get is SL2 at level 0. So these are the currents. So if I calculate the OPs, for example, I get the SL2 at level 0. So what is happening here is that in the Vakimoto realization, if I just put the background charge k equals to 0, the background charge becomes I, and that scaling in the Vakimoto, I am fermionizing it to a p theta. That's the idea. And in these 2D angles, the central charge should be 0, at least for the free chiral 2D angles. So this is also might not be too strange that the k is 0 from the Brown-Hahn formula. So then the idea is that I have an AdS inside this string theory, and the 2D angles is living on the conformal boundary of this AdS. So for example, if I have a target space with any genus, I should do some orbifold on the worldsheet so that I get the 2D angles is living on the conformal boundary. Just a reminder, also this gamma represents the boundary coordinate on the worldsheet. So some checks that we have done. The first check that I already mentioned is to put the target space on the torus. So in this case, as I mentioned, there is no branch point. I should just consider the connected compact coverings of the torus. And then we can calculate the partition function in this case exactly by doing an orbifold on the worldsheet. And that's the final result. And this exactly agrees with the David Gross Washington Taylor result. Another check that we have done is the covering a sphere of like worldsheet being a sphere, target space a sphere. And in this case, we can calculate the cohomology. And the cohomology, including the spectral flow, consists of these operators. And then we can calculate the correlation functions. So from the trivial symmetric orbifold side, this should just count the coverings. And we have checked that for a generic covering map, this is just 1. This is just counting the covering maps. So that agrees with the space-time. Okay, so some comments and future direction. First, we haven't yet done the case of higher genus target space. This should be obtained by doing some orbifold on the string theory and seeing if we can reproduce the partition function. Another thing is to turn on the coupling. This is complicated, as you heard. But for example, just a simple branch contribution should be some deformation on top of the other deformation that I was discussing of this sort. And another thing that is interesting is to find a more natural interpretation of this deformation that I discussed from the worksheet, so that I don't have to perform any deformation. And another thing is to, in this formalism, is combining the chiral and antichiral sector. And another thing is to consider the instanton expansion of 2D angles and see how that can be reproduced from the worksheet. And another thing, as you just heard, is to consider the Wilson loop expectation values from the worksheet. Thank you.
Questions? Yes, Tom.
There was a paper last year by Eric Sharp and Tony Panther about the gross-Taylor string theory. They argue that, if I recall correctly, there has to be some higher form symmetry in the gross-Taylor string, which is related to worldsheet instantons. And I think this is related to a very large non-invertible symmetry on the pure Yang side. Does this play any role in your discussion?
I don't know.
Okay.
Yeah.
Perfect.
Yeah.
So when you turn on the coupling, can you see if you get the correct area terms in some example of
Yes.
polynomials in the area or just exponentials?
Just the simple branch point contribution, that I think we can see. Yeah, but the collapsed handles and the tubes, that I don't know how to do.
Any other questions? Not, let's thank Kiarash again.